Okay, I think we're online. Is my mic on? Okay. Again, super sorry about what happened. I think from what I know from the department, they moved us from 105 Northgate back to 10 Evans, but then the Central Campus didn't know that we were back in 10 Evans, so they thought 10 Evans was open. They gave it to Econ 100 for their exam, and I didn't want to kick them out of their exam room because that's kind of mean. So instead, we got kicked out of our room, and then we got kicked out of 105 Northgate because the School of Journalism used that room like ad hoc, and so yeah, now we're here. So let's see, 40 minutes, and the problem is I do want to get through as much as I can because you will need some of the material for today's lab. And I don't know whether we can make that happen, but maybe we can. So what we're going to do is I will go through my slides once at a very high level, and then start going through them in more detail. And we'll try to do like a breadth first search over my slides if you're familiar with that terminology. Okay, so I'll try to give you like the main takeaway. I'll like spoil all the cool takeaways that I have from my slides like right from the get-go, and then I'll try to layer on some more nuance and some more detail. And then we'll see where we are in 40 minutes. If you feel like you're unsure, if you feel like you want some more like explanation for different things, what I can do at the end of class is take a list of questions. If we can't answer all the questions, I can just take a big long list of them, and then I can try to like do a little screencast after the fact and try to make sure we get everything. Okay, so that's kind of the plan. Thanks for working with me. This wasn't in my control, but I'm doing my best, and I hope you can do your best too. Okay, so here we go. We're going to be talking about inference for modeling today. And inference for modeling essentially means take what you learn in Data 8 with the Bootstrap and apply it to modeling. And so the first 1 hour of today's lecture was originally planned to be a review of Data 8 Bootstrap. And what I'll do is I'll just give you the main takeaway and usefulness of the Bootstrap. Okay, so here we go. Some announcements. Okay, so again, in inference, what we're trying to do is take our sample, compute some estimation from our sample, and use that to make some conclusion about our population. And we said that in this slide that I showed you from a few weeks ago, we had this particular sample, and then we computed the sample proportion or sample mean to be 0.51, and we said this could be a sample of US voters, and we asked them whether they would vote for Hillary or for Donald Trump, for example. Okay, so we took the poll, and we got 51% voted for Hillary, and because we know that this particular estimator is unbiased, what we can conclude is that our population parameter is pretty close to our sample's proportion. So this is one of the neat results of inference, which is that even if you have a sample, you can make some conclusion about your population. Okay. Now the issue with this estimation here, 0.51, is that it's almost certainly wrong. And it's almost certainly wrong because our sample isn't our population, and so chances are pretty good that we won't get 0.51, we might get 0.50, we might get 0.52, we might get 0.49, right? So we might get 0.51 or something relatively close to 0.51, but maybe not something too far away if we have a large enough sample. Okay, so the basic idea here is that we're doing estimation, and instead of just saying this is our answer, what we want to say is these are a range of values that I think our answer could reasonably be in. Okay, so instead of just saying our population proportion is 0.51, we'll say our population proportion we think that our proportion lies between 0.48 and 0.53, for example. Okay, so that's the idea behind doing a confidence interval. And the confidence interval, let's see here. Yeah, so the confidence interval is like the range of values that we think the population proportion can be in. That's pretty much what it is. So I'm going to skip this text here, skip this variance thing here. Okay, skip some scary math. Okay, here we go. So what we like to do is say, you know what, I'm not going to show this slide. So what we like to do is say essentially that we'll imagine in our minds taking a bunch of samples. Okay, and for every sample, we'll take the mean of that sample. So we have a bunch of sample means. And if our estimator has high variance, meaning that it varies quite widely, then what we should say is, since our estimator has high variance, we're less certain about our estimation, and so our confidence interval should be bigger because we're less certain about where our population parameter could be. If we're very certain, if we're very accurate all the time, then we're quite certain about where our population parameter is, and so our interval will be smaller. Okay, so the intuition here is that I have here a variance equation. But your takeaway here is that high variance means big intervals, low variance means small intervals. Okay. And so what we want to do is try to estimate the variance of my estimator. Okay, so here's an idea that we could do, which is from our population, take a bunch of samples, compute sample means for each sample, and then the variance of those sample means is what we call the variance of our estimator. Okay, so for example, here I have 9 samples that I drew from my population. I can take the sample means of each one. Here are my sample means. And the variances of each sample mean, variances of all of these 9 numbers here is what we say is my estimate for the variance. Okay, so there's like multiple levels of estimation here. And the hardest thing for a lot of people to understand about this procedure is what are we taking the variance of? Okay, so the variance of a random variable, okay, I'm going to go back a slide real quick. So the variance of a random variable is this formula here, which we've seen before. And it turns out that if a random variable is our estimator, then we say that the variance of an estimate, like we have a special name for that. We call it the sample, we call it like the estimator variance. Okay, so basically, X could be anything. So X could be a point drawn from the population. It could be like rolling 2 die, taking their sum. And if I let X be an estimator, then we say, then this variance has some special meaning and some special use for us. Okay, so if X is a point from the population, that's different than the variance of the sample means. Okay, so we can look at our whole population and look at the variance of all the points within the population, and that's what we call like the population variance. But if we do the procedure of taking many samples, taking all of their means, and then looking at the variance of the sample means, that variance will be smaller than the population variance. Okay. I'm going to show you a quick demo, and I think what I want to do here, what I've done here is I have the code for the demo. I'm not going to write any code because we don't have time to do that. But what I'm going to do here is say my population is just all the numbers from 0 to 10,000. Okay, so just all the numbers from 0 to 10,000. Here it is. Okay, and we might want to estimate the population mean. And so what we're going to do here is I'm going to say, here's my population, and let's pretend that we don't know this number. So what we can do is we can say, well, if we try to do an inference procedure, we should be able to get pretty close to 5,000. And that's kind of our goal. In most cases, you won't know the population, in which case you won't know 5,000. But for today's demo, we know the population mean, just so we can compare how good our procedures are to getting this mean. Okay, and so for example, you might imagine that if I draw a sample from this population and take the mean of my sample, I get pretty close to 5,000. But not exactly 5,000, because our sample is randomly drawn. So if I run this again, I'll get sometimes below 5,000, sometimes above 5,000, so on and so forth. Okay? And so what I can do is I can take many draws, many samples, and take the means of each sample like I'm doing here. So essentially, I can rerun this cell many times. And these are the means of a sample of size 100. And so I can plot those means in a histogram. So I can run that, and I can see that for samples of size 100, most of my samples have a mean pretty close to 5,000, but some of them get a mean of over 5,500, and some of them have a mean of under 4,500, but not too many of them. Okay. Now this distribution is different from my population distribution, right? So my population distribution is just the numbers from 1 to 10,000. The values in my population is just like a flat histogram because we have one number each from 0 to 10,000. But if I take samples and I look at the means of the samples look normally distributed. And this is a consequence of the central limit theorem. Okay. Now, if I increase my sample size, the variance of my estimations goes down. And if I increase it even more, I get a very small variance. Okay. And so what we do is we say, if I had access to this distribution, I could create a confidence interval. And the way I create a confidence interval is I say, find the two endpoints that keep 95% of my values. So in this case, my confidence interval would go from, let's say, like 4,200 to maybe 5,800, like so. If I have larger samples, my confidence interval gets narrower. So here we go only from 4,600 maybe to 5,400, like so. And if I increase my sample size even more, my confidence interval gets very narrow. Okay, so the idea here is, as my sample size gets bigger, my confidence interval gets smaller because I'm more certain where my population parameter is going to be because I know that the spread of my estimator will not be as big as it was before. So if I increase my sample size, the spread here gets smaller, which means I'm more certain about my estimation. Okay. Now the problem is we can't actually do this. And the reason why we can't actually do this is because it's usually not very practical to go back to the population and keep taking more samples from it. Right? So if I'm doing an election poll, it's a pain to even get one sample because I have to like kind of travel all over the US, talk to people about who they're voting for, or have them mail ballots in, like mail mock ballots into me. And to do this procedure requires me to do this poll like 1,000 times. And doing a poll 1,000 times is just a huge amount of work. And so what we're looking for is a way of guessing this distribution without actually having to go out and take more samples. Okay, so the intuition here is the Bootstrap is a way of estimating this distribution here so we can make a confidence interval without having to go out into my population again and keep taking like thousands of samples. Okay, and so the key idea behind the Bootstrap is that if our sample looks like our population, then we can pretend that our sample is the population. Okay, we can use what's called the plug-in principle and just say, well, these two things look close enough, so let's pretend the sample is the population and take more samples from our original sample. Okay, so the idea here is instead of taking samples from our population, we'll resample endpoints from our original sample with replacement, and this is what we call our quote-unquote sample from population, but it's our best guess at getting something like that. Yeah, Danny?
Is a way to ensure that your sample looks like the population, is that just by doing an SRS?
Yeah, so usually if you do an SRS here, this usually only holds when you take a random sample, and that usually means doing an SRS or some variant of it, like a stratified sample or a cluster sample. Okay, yep, so we can really only make this intuition statement if our sample is drawn randomly, because otherwise we don't have any idea whether a sample really looks like the population or not. Okay, so here's the idea. Oh yes, I do like this. Okay. So I mentioned before that what we would like to do is go to our population, take a sample, take many samples, find the means of each sample, and make a confidence interval based on those means. Okay. And what we'll do instead with the Bootstrap is take one sample and draw samples, resample that sample to get what we call Bootstrap resamples. And then we can compute the means of these resamples, and that is our estimate for that distribution. Okay, so these two things, so this on the right-hand side is trying to estimate what's on the left-hand side. And if our sample is drawn randomly and it's relatively large, then we'll do a pretty good job most of the time. Okay, skipping this. Let's see here. Okay, so what I want to show you now is kind of another visual representation of this procedure. Okay, so on this slide, I have the sampling procedure that we have without the bootstrap. So here is my population, and here are 5 possible samples from this population. So each of the histograms shows 1 sample, and for every sample, I'm going to take the sample mean. So the sample means I've labeled here in X bar. So here are the X bars, 1 for every sample. And if I take all the sample means and plot them on the histogram, then I get what we call the sampling distribution of my estimator. Okay, so this is a special distribution. It's a distribution of my estimations. And it's a distribution that I use to make confidence intervals. Okay, so I don't make a confidence interval from this distribution. I make it from my sampling distribution. Okay. Now the thing about the bootstrap is that right here, what we have is 1 sample. And I can bootstrap this sample by resampling it with replacement. When I do that and draw the distribution, I notice that the distribution is not actually centered at the population mean. The reason why it's not centered at the population mean is because if we pretend that my sample is the population and we're drawing from our sample, then all of my estimates will be close to my sample mean and not my population mean. Okay, so the reason why this distribution is not centered at mu, so mu is our goal. But this distribution is not centered at mu, and because there's some imprecision in saying that this sample is a population. Okay, so this discrepancy here arises from the estimation that we're doing here by saying that our sample is our population. So there is some discrepancy, but the important part here is that even though the center is not exactly right, the spread of this distribution looks like the spread of the one before. So I'm going to show you this slide. I'm going to go back a slide. There. Okay, so here's the spread, and here's the spread. Okay, so the key thing to note here is that what we're really interested in is the spread. And because the spreads are similar, we can use this distribution to make confidence intervals. Okay. So to make a confidence interval, what I'll do is I'll do this procedure here, and then my 95% confidence interval will be the interval that contains 95% of my values here. Okay, so now, let's see. What do I have here for a demo? I'm trying to watch my time. Okay. I'm going to skip this. Let's see. Okay, so if you look through my demo for today, you'll notice that here I'm showing let's see here. Here I'm showing the endpoints of a confidence interval that I create from the Bootstrap. Okay, so most of my Bootstrap intervals will start at 4,000, between 4,000 and 5,000, and end between 5,000 and 6,000. Okay, so even though we know that our estimation won't be right all the time, on average, our endpoints of the interval will have 5,000 in the middle, but not always. Okay, so there's some orange bars here that go below 5,000. So these are intervals that do not contain our true population mean, 5,000. And there's some blue. Actually, I don't think there are any blue on this particular plot. But if I run this plot again, you will see that sometimes we miss the population mean, but most of the time we get our population mean. Okay. Any questions? Okay. So I'm just going to show you my little demos here. Let's skip the words, just show you the pictures. Okay. So to make a confidence interval without the bootstrap, I have my population. I take a sample, take more samples, compute the confidence interval, and I'm assuming here that I just wrote some Python function that computes the confidence interval. And here's my interval for this particular sample. If I do the confidence interval on many other samples from my population, then I'll get different endpoints. And what I'll see here is that these endpoints are numbers. And if my real population mean is this value here, then what we hope is that the confidence intervals contain the population mean. Okay. And so what we'll say here is that if our confidence interval is 95% confident, then we expect that about 95% of these intervals will contain theta star, our population parameter. So that's the meaning of confidence. The meaning of confidence is that if I repeatedly take samples from a population and compute confidence intervals from those, then 95% of those intervals will contain theta star. Now, it does not mean that one particular interval has 95% chance of containing theta star. But it does mean that if I draw another sample from the population and take an interval take another interval, that interval will have a 95% chance of containing theta star. Okay, so the difference here is if I already have an interval, then there's nothing random about that interval if I already have one. And so if I already have an interval, it either contains theta star or it doesn't. But if I go back to my population and draw a sample, now I have some randomness. And now I can make a probabilistic statement about that interval. And so the confidence in the confidence interval is referring to this probability that arises from this entire procedure and not any one part of it. Yeah, question?
So let's say we were dealing with some parameter and we didn't really have any kind of analytical formula like the sample mean. Is it possible for us to get a confidence interval from a single sample without using Bootstrap?
So the question here is, let's see, without the Bootstrap, can you always make a confidence interval? The answer is no, but in most cases you can. Yeah. So most parameters of interest, like the median, for example, or like the coefficients in linear regression, have some complicated. If you make some assumptions about those coefficients, you can do some complicated math and get out the confidence interval. But in this class, we'll just use the Bootstrap because it's general and works for most things. Yeah. Okay. Now the Bootstrap, what the Bootstrap does is it gives us a way of making this interval. Okay. So here, I'm going to take a look at the CI function. And the way I make the CI function is I take my sample, I resample it with replacement. I compute the sample mean for every single resample. Here are my sample means. These sample means are distributed. And what I can do is take an interval that contains the middle 95% of these sample means if I'm trying to get the 95% confidence interval. Okay. And so this is the Bootstrap procedure for computing a confidence interval. And the claim here is that if I take the middle 95% of these values here, it turns out that most of the time, 95% of these confidence intervals will contain the population mean. This is also known as the percentile bootstrap. And let's see. Had a demo. We'll see if I'm going to do it, because the demo takes a little bit of time to run and I do all the bootstraps. I'll just go through the visualizations and talk you through it. So let's see here. The neat thing about the bootstrap is that it works not only for the sample mean, but for many other types of parameters as well. Right? So I can do the bootstrap, and I can estimate the sample mean and make a confidence interval for the sample mean. But the neat thing about it is that it's not restricted to the sample mean. I can do it for the median, and I can estimate the population median. Here are the confidence interval widths for the median. I can even estimate the standard deviation of my population by bootstrapping the standard deviations. So if I do that, I can see here that my estimate for the standard deviation is that it lies between 2400 and 2900. And indeed, the population standard deviation does lie between these two numbers. Okay. Let's see here. Now the bootstrap doesn't do so well when you're estimating skewed parameters with skewed sampling distributions. So here's the 99th percentile of my population, which is 9900. And it turns out that if I bootstrap the sample and look at the distribution of my 99th percentiles, I don't really get what we think of as a normal distribution. So if I make a confidence interval, it turns out that that confidence interval will not contain the population parameter most of the time. Okay, so here I have 100 confidence intervals, but only 67 of them actually had the population's 99th percentile. Okay, so it turns out that the bootstrap is really good, but not always great. If you notice this pattern, if you don't notice a normally distributed sampling distribution in your bootstrap distribution, then you're going to have a problem with the bootstrap. There are also problems that arise when you have very small samples. And there are ways of coping with these difficulties, but you should know about the difficulties so that if you do it yourself, you'll know when you can use the bootstrap that we taught in this class, or whether you need to go look for something more sophisticated. Okay. Likewise, the maximum of the population is pretty hard to estimate with the bootstrap, or with our percentile bootstrap. Running this code shows me that exactly 0 of my confidence intervals found the maximum of the population. Okay. I'm not going to have you fill out attendance to save time. I'm just going to give everyone a point for today. Okay. So the basic idea behind the bootstrap is it's a general technique to make a confidence interval from a point. Okay, so the idea here is if I have one sample, I only have one sample mean. I know that sample mean is not exactly my population mean, but it should get pretty close. And the confidence interval is a way of quantifying how uncertain I am. Because the wider my interval, the more uncertain I am. And the narrower my interval, the more certain I am. Okay, so that's kind of what we're aiming for confidence intervals. And the key idea behind the bootstrap is that the bootstrap lets us make confidence intervals even though we only have one sample. Okay. And so we can apply this technique to modeling as well. Okay, so in modeling, oftentimes we only have point estimates, but we can use the bootstrap to make confidence intervals around those point estimates. And when we're applying or extending the confidence interval use cases to stuff that we haven't seen before, it's important to understand what we're trying to estimate and what's our parameter of interest. Okay, so before we kept it pretty simple. We said we're interested in the population mean, we're interested in the population median, and now what we're going to do is extend that to modeling. So now we can say, okay, well, in modeling, I have a training set and a test set, and if we assume that both of these are random samples from the same population, we might be interested in the accuracy of our model on the population. Right? In other words, we can take our model and we fit it to some training data, and we want to know how well will my model do when it graduates from my little notebook here and goes to do some stuff in the real world. Okay. And the problem here is that we can't know this. We can't know the accuracy of the model on the population unless we have the population, but we can estimate the accuracy of the model on the population via the test set accuracy. Because the test set accuracy is a random sample from my population of interest, and it wasn't used to train my model. So my model won't overfit to my test set. Okay. And if I look at my test error and compute the test error of my model, that's a point estimate. Right? It's a single number that says, this is what I think my model's population error will be. Okay? And because it's a point error, a point estimate, what we can do is draw a confidence interval around that point estimate. So here's the idea. we fit the model on X train and Y train. We make our model predict on the test set, and we compute the accuracy on the test set. And since the test set is a random sample from a population, this is an estimator for the population accuracy. Okay, so it's quite meaningful because this right here is our guess at how well our model will do on data it's never seen before. Okay. And so what we can do is, okay, so first of all, I'm talking about accuracy here, but this idea also extends to test error. So if you look at the mean squared error, you can also bootstrap that and get a confidence interval. And here we're bootstrapping the accuracy of a classifier and making a confidence interval around the accuracy. So in this case, since we're interested in the error on the population, we'll resample our test set because our test set is representative of data that we haven't seen before. So we'll resample our test set only and look at the model's error across all the resampled test sets. Okay, so I have here a classifier using the cancer data set. I have here a training set and a test set. And right here I have the test accuracy for this model. So it had 93% accurate on the test set, and if I make a confidence interval, I see that I can estimate that my population test error or test accuracy will lie between 89% and 96%. Okay. We can do the same thing in comparing two models. Right? So if I have a training set and a test set, and I fit two models, I can ask the question, which one does better on the population? And again, I can't know that, but I can estimate it. And the way I estimate it is I fit both models on my data. I look at the model's predictions on the test set, and I compute the difference in accuracy between the two models. And this right here is the estimator for the difference in accuracy of the models in the population. Okay, so we expect that if the models do equally well in the population, that this estimator on the bottom here will be close to 0. And if one model does better than the other, let's say model 1 does a lot better than model 2, we expect that that last line there will be large. And vice versa, it'll be negative if model 2 is better than model 1. And that is also a point estimate of the difference in accuracy. And so what we can do is, again, bootstrap the test set to make a confidence interval for that difference in accuracy. Okay, and you may recognize this. We've done something similar in data 8 where we looked at the difference in means. And the idea there is that if our confidence interval for this difference contains 0, then the models are not significantly better than each other on the population. That's more or less what we would conclude. Okay. And so here again, we resample a test set and look at the accuracy differences and make a confidence interval for the accuracy differences. Okay. We can also look at the parameters in linear regression. Okay, so we have here a training set and a test set. If we fit a linear regression model, we might be interested in which associations are meaningful. And in data 8, what we did was we bootstrapped the linear regression for just a one-dimensional case, right? And we said that we have a scatter plot, and if you bootstrap the scatter plot and fit many regression lines to that scatter plot, you can make a confidence interval for the slope of the line. And if that confidence interval contains 0, then there's no significant association between our variable of interest and the variable we're trying to predict. And the same idea applies when we're doing multivariable linear regression. Okay, so here, I fit a model. I look at the coefficient for a particular feature, and this is the estimator for the slope associated with that feature in the population. Okay, so in linear regression, what we're assuming is that in the population, data are generated according to a linear model. And if we make that assumption, this estimator here is our best guess as to the actual slope associated with that feature. Because we're making a best guess as to the slope, we can again do a confidence interval. But the way we do this confidence interval is we resample the training set. Because we're not making a statement about the population error or population accuracy, we're making a statement about if I drew many samples from a population, what's my best guess as to the slope of those linear regression models? Okay, so again, if the confidence interval for the slope contains 0, then the feature here is not significantly important for the model, just like for data 8 in the one-dimensional case. Okay, and we can do something similar for logistic regression as well, but it's easier to kind of visualize the slope being 0 for linear regression, so that's why we're doing that. Okay, so here I have a data set on Boston housing prices, and what I can do here is try to predict the house value based on some features. And what I can do here is look at one particular feature, like the crime rate of that neighborhood, and if I bootstrap the coefficient for the crime rate, what I can see is that this confidence interval doesn't contain 0, and it contains negative values, so it looks like there's a significant negative correlation between my crime rate and the housing value. In other words, if there's more crime, the housing values go down, and it seems like that association is significant. It's unlikely to have happened by chance. Okay, so I really rushed through this lecture. I have some caveats that I mentioned before. So here's a summary of what we covered. We have a few minutes, so I did want to take a few questions, and if we get overwhelmed by questions, then I'll try to answer them offline. But I did want to try to finish in time, and it looks like I succeeded. And I can take questions about things you're confused about with the Bootstrap. Yeah.
Why can you assume that the sample distribution represents the population distribution?
It's a good question. So the question was, why can I assume that the sample distribution looks like the population? Right now we have to right now is something that I state that we just do because it does work out like that. If our sample is randomly drawn, if you want to know, the real reason why is essentially that if you draw a sample at random from the population, then you can think of the sample points as random variables drawn from the population, and when you do that, a lot of each individual sample point will have the same distribution as the population sample point, as the population points. That's roughly the reason why. Yeah, but it's a good question, and one that we can only make if our samples are randomly drawn, because only then can we make some statements about our sample points being random variables. So if they're not random variables, and thus we can't do any of the neat statistics that we do for random variables. Yeah, question?
Why do we resample the training set instead of the test set?
Yeah, it's a good question. So why do we sample the training set instead of the test set for linear regression? The reason why we resample the training set is because we use our training set to make our estimate. So we use our training set to make our estimates for the slope. And so because of that, we have to resample the training set to get more estimates for the slope. We don't get our estimates for the slope from the test set. We use our test set to look at the error or accuracy of our model on the population. And so when we're interested in those quantities, then we'll resample our test set because that sample makes the estimators for that particular population. So it's all about knowing what population you're interested in and then resampling the sample that comes from that population. Yeah?
What is the negative confidence interval imply? It told us that there was some negative association. So when it then contains the
Yeah, so what does a confidence interval of negative values imply? For linear regression, a confidence interval that only contains negative values means that even if I took multiple samples from the population, it looks like most of the slopes will be negative. And so if most of the slopes are negative, then I can say that one variable makes the other variable go lower. So if I increase crime, I decrease my home value. And you might also imagine that if I increase, let's say, I don't know, number of lawns on a house, then I also increase the home value, and I would expect the slopes there to be positive, and I would expect that the confidence interval will contain positive values. Again, if there's a feature that has no influence on this, if there's a feature that has no real impact on the home value, if I fit a linear regression model using that feature, the slope will not be exactly 0, but it might be close to 0. And so what we say is that if our confidence interval contains 0, then that slope is close enough to 0 that we think that it probably could be 0. Okay. Thanks for bearing with all the room shenanigans, and I'll see you on Monday.